let's see. So the next thing is the discussion session. And so this is on time series analysis and time domain modeling. And it will be led by Barbara DeMarco and Phil Uttley.
Okay, so this is about timing. However, so as it's clear from previous session and in general in the last year, it is really difficult to, when it comes to discuss binaries like microquasars, black hole binaries, and neutron star binaries as well. It's really difficult to separate the timing and spectral properties. This is just because we cannot get a complete picture of these the physical processes that are ongoing in these sources just by considering spectral and timing separately. So with Phil, we decided to focus on spectral timing again. And so when we all know what spectral timing is, but maybe many of us some of us may not have the feeling of how difficult might be to deal with spectral timing analysis and modeling, especially for those that started to this kind of analysis years ago. So just to give you an idea, when you need the spectrum, you just reduce it from you use tools that are already integrated in reduction softwares, and you put it in XSpec, and you get a huge library of models, and that's it. While for spectral timing, for many years it was quite difficult, because you had to build your own routine, you didn't have models. So to get on the discussion, we would like to start off with a little survey.
Yeah, let me just try and get this running. Hang on.
Yes,
Keynote.
okay.
I don't normally give presentations with Keynote, so I'm just trying to get it to share. Oh, okay. So you can see.
Yeah, here it is.
Great.
Okay, so this is just.
But if I play.
Yeah.
This is annoying because now I can't see. Now I can't even see my mouse pointer.
You can't. Okay.
Yeah, I'm gonna. Is this better? Let's just.
Well,
not
I think it's okay.
And we'll just.
You can leave it like this. You can leave it like this.
Yeah.
Okay, so we want to start with a little survey, just to get you more involved, to get this discussion more interactive, and also to get an idea of what's your feeling about spectral timing. So I would like to ask, so raise your physical hand or your virtual hand. How many of you do use spectral timing methods? Have used, will use spectral timing? Okay. So we have many in the room.
Yes, on Zoom. Oh, I see a lot. Yeah.
Okay.
I'll just quickly count.
So the other point is that which code do you use for spectral timing analysis? No. So now we have public codes that are, we heard about Stingray. So the question is whether you use public codes or you developed your own code. And in this case, we would like to know why. And or you just use the code that, for example, was given to you by your supervisor or someone else.
So I guess maybe to split it up, because you need to put your hands down first.
Yeah.
So put your hands down.
Put your hands down.
and then maybe just focus on the first question would be the public code. Are you using a public code like Stingray or Kronos?
So if there is someone, yes, if there is someone that wants to comment. So they have some comment on this,
so
wants to reply publicly to these questions.
If I'm using something that is kind of like our own, but still public, right? ISIS things, this is still a public code, right? Or not?
Sorry, say it again.
So if I use something like the ISIS scripts, that's right, it's public. So would that still fall under public code, right?
Yeah,
yes.
I think so.
So yeah. Okay, so the next point is modeling, which is another important step to get an interpretation. And we now have quite a few public models or non-public models. So there are groups that are using their own models, but these models are not public. So the question here is whether you ever tried to fit your data with spectral timing models, and if so, whether you got whether you got amazing results or you got results that didn't convince you, and in this case, why? And if not, why? For example, if it's too tricky or not. So the idea here is that if you have comments now that if you want to reply now, okay, so we can discuss this. Otherwise, we created a channel on Slack where we can go on with this discussion and maybe like exchange opinions on current softwares, current models, and so on. This is before going to the more scientific questions. So is there, yes. So we have Matteo here.
So one difficulty that many people have, we see it all the time with the issues in Stingray, is that maybe there is a paper that had a result and they cannot reproduce it. So is it a problem of the code? Is it a problem of the original paper? Is it a problem nowhere, just because maybe the assumptions are not clear either in one place or the other. So I would really like, from the point of view of someone who's trying to develop public code, I would really like if people doing this kind of their own modeling were a little more open in describing not the fact that you are taking an FFT and calculating a time lag and or calculating some higher order product, but on the subtleties, like exactly what did you do to clean the data? Exactly what did you do when there was some non-valid number appearing in your data, or some strange number coming out?
But are you suggesting to put this information
More
like
publicly in
okay.
general? Either, I mean, not everybody want to make their code public, but at least there should be more openness. I'm not accusing anyone, mind. It's just that it's a huge work, and I realize that people sometimes don't do that because it's a huge work. But it will be.
Do you mean the analysis code, like so the actual code to get the timing products, or do you mean the modeling type stuff? Because I think maybe that's also especially for the analysis, right? That a lot of people have their own bespoke software, right?
This is already in the first part, so I mean, it drips down to the modeling, because if you don't have this in the product, even more in the modeling, this is a problem.
Ulo has a question.
Yeah, hi. I wanted to comment on this. Well, personally, I use my own code to from like the reduction and down to the modeling, as you heard in my talk, of course. But like staying on the reduction, I use my own code, but I think is not the best procedure. I think we should probably put the effort together and decide maybe. I mean, I think Stingray is a great tool, and probably we should like focus our effort in like helping developing this tool. So if all the supervisors suggest to their like new PhD students, new postdocs to that start spectral timing to use a Stingray, I think we can create a tool, a really great tool and comprehensive that and we can do the reduction in the same way. So I'm guilty myself of using something that is not that is like developed by by myself when I started my PhD in Fortran. So you can imagine, I think we should put our efforts together and decide to develop one comprehensive tool. This is my view, at least.
There is a question from Jan Beams here.
Yeah, John Williams here. Phil will probably know the rant that's now coming, and I'm disagreeing with what was just said. I think we do have a general problem also in this discussion about not distinguishing between computer languages and methodologies. If the analysis that you do depends on the tool set or on the language that you're using, be it Python, be it Fortran, be it Julia, be it whatever, then you probably have a problem. And you probably have a problem because this means that you're concentrating on your tool rather than on the science that you're trying to do. A big problem, I think, that we have, especially in time series analysis, is that time series analysis is really, really complicated. So we have problems because it takes a real effort to understand what time series analysis tells us. Saying that because I use X, Y, or Z as a tool and asking purely for black box to be a bit provocative, I think is not the right question. The right question is, what is the science that I get out of my data, and then use the tool that's appropriate for answering that question. As soon as we try to do a one-size-fits-all toolbox, I think we have a problem. Having said this, I think it's extremely important to have verified tools that people can use. But I think we have to be very, very careful not to be fixated on the tools. So I'd suggest not to have the tool discussion, but rather to have the discussion, what is the science that we can do with these tools?
Yes, this is the second part, actually. So maybe we can go on.
Okay, Greg, did you have a quick comment?
Maybe we have another, yes.
Just a very quick comment is that, if you think about how hydrodynamic simulations work, they have their sort of standard test cases. And so one of the things that would be fairly useful, regardless of whether you're on which side of this debate you're on, is if we come up with our sort of standard test cases and have that as being sort of the litmus test for both new and existing existing tools to make sure that everything is in fact working.
Yeah, I think that's really important. I was also thinking that same thing. From what Jörn was saying, that yeah, there are definitely cases where people's results seem to disagree, right? And they shouldn't, because it's just mathematics, it's the Fourier transforms and stuff. So this goes on to the point about, yeah, what Matteo said about people explaining what they do with their data. But yeah, if we have agreed kind of results, if you like, with certain time series data, then everyone can check their own code as well. And that's a good way to go forward. Maybe I can then step on to, because Barbara, do you think that's okay, Barbara? We can move on to
the that's okay. That's
next
okay.
slide. So let me just see. Okay. Okay, right. So now we come on to more the kind of, if you like, the physics side of it, which is that there's a whole bunch of questions that I think we've already covered a bit in this meeting about things that we don't really understand, right, with regard to interpreting the timing data. And what we'd like to do is produce models, and we've already seen examples like Guillermo's talk and others earlier, Ed Nathan's talk, and about how we can model, these data that we have. And there's a whole different question about making modeling packages and making a kind of XSpec for spectral timing or anything like that, which is a different story. But just in terms of physics, I think it's clear that we're missing a lot. And so I just give a kind of list here. I'm not going to go through them, but I just maybe if anyone wants to comment on if they think there's a particular issue that's important, because we touched a bit on with Gulo's talk about this issue of the reflection models and maybe what comes out in soft X-rays, in X-ray binaries from reflection. There's also the questions about QPOs. Obviously, there's the issue about the type of QPO model it is. and from the MHD point of view, what you get with these propagating fluctuations. But I'd like to maybe, it'd be nice to hear any comments from the audience about what they think is important, and perhaps what we'd like to have from the theorists and the numericists, you know, in terms of some sort of things that we can then bolt into models and better interpret the spectral timing and timing data. I don't know if anyone has any. I think Sarah has. Greg, no. Let's see. Does anyone have any comments on that specifically? It depends how many of the theory folks you've got left, I guess, as well, but maybe from the point of view of the observers or the people trying to interpret the data.
Yeah, I didn't want to talk too much, but if nobody else is saying anything, I could just mention, like, I think one of the things that we need, at least from the theory side, right? I mean, we need long running stable simulations that we can make, you know, with radiation in it, so that we can make accurate time series. And so for that, like, it's actually, you know, early days for that. We've already done a bit of that for the Event Horizon Telescope related research, where, for instance, Koshik made these really long light curves. And then they were compared to statistical distributions of the variability, like the cumulative distribution functions and so on. And so I think there's a lot of potential there, but for QPOs, it is quite difficult. And of course, you've seen, you know, Matthew and other people, Vlodek's group, you know, people are working on this, but it's not going to be easy to get the data out of the simulations. And I think, yeah, well, anyway, that's where I'd really like to see a lot of the work going for comparisons.
Yeah, I think that point, because there was a discussion about that with Jibwe Masoke's talk, right? Where that she told us about the QPO, the kind of like a high frequency QPO that appears due to this disk tearing, and this idea with that it's a specific. It's not only a question of picking out a specific frequency. You have to make enough emission modulate at that frequency, and I think that's always been the problem, that people can generate frequencies, but making stuff emit enough light that we actually see those as real QPOs is the challenge.
Can I just bring up one point that I think has been under discussed at this meeting? I hope it will come up maybe later, but I mean, we haven't really talked much about the infrared QPOs. You know, it's obviously a rare detection. There aren't that many cases of it, but I think that this is super exciting because it's telling us that something extremely, you know, rigid magnetic fields are basically jiggling from the disk all the way out to whatever 10⁻³ gravitational radii where that light is coming from. And that is a really huge clue also for theory. So, I mean, I would like to see better data constraints on the not just the 100 millisecond lag to that zone, but actually the QPOs out there.
Yeah, right. I don't know, maybe Poshak will mention this in, I don't know, he's online, I think, maybe in his talk.
I don't know if Federico is on right now, but Federico.
Exactly. Sorry, that's what I was going to say. Federico might mention it. I don't intend to talk about.
Yeah, I will present some things. And
also, I think Sasha touched upon it in her discussion, but there wasn't much time at that point.
I will have some discussion on that. I don't know if you want to discuss it now, but.
Yeah, but well, I guess, I won't preempt your talk, but I guess the question there is really about the emission, right? Because at the moment there's models, sort of analytical models for this, but it's actually merging all this stuff with the GRMHD, because you have the nice simulations that Matthew did with showing precession, where you have something that looks like the jet that's also precessing, like with a Lenser-Thirring type precession. And so you can see that the jet is tied to the flow in that sense. So getting that with all the physics, with the emission self-consistently included, that's going to be super important, I guess, for this.
I mean, right, so, because, oh, sorry, I was just going to mention, I mean, Jibwe's paper, of course, they're just using the accretion rate as a proxy, not the real, the real X-ray emission. So that you have to ask yourself if that's going to actually translate through. And I think it's the same with the simulations that of the tilted disk. We actually had some jet simulations where we saw kind of some QPO type behavior going up the jets, but we couldn't run them long enough and keep them stable long enough to actually get like a decent signal. So there's a lot of technological problems.
Yeah, I guess we're limited by computing power and Moore's law and things as well. Does anyone have any more comments on this, on the actual physics, physical understanding, or what they think might be a priority for better understanding the timing and spectral timing information? And of course, we can continue in the spectral timing, maybe, you know, if you want to think about it and add stuff into the spectral timing channel, because these are great things to keep thinking about going forwards as well, and how we can improve our models. So just to end, I guess, there's a couple of more points about, yeah, what are the obstacles? I mean, I guess the big question is fitting the models. Maybe I can do the people who have been doing this, so like Gulo and Ed, are you using your own code, like, you know, separately, or are you doing this kind of with the Clusian XSpec to actually make these fits happen? Or are you actually doing it sort of separately from XSpec, for example, or ISIS or Sherpa?
You're talking about the fitting process.
Yeah. So I mean, it's an XSpec model, right? As far as I understand.
Yeah, it is. It can be loaded in XSpec or ISIS, and yeah, it's XSpec or ISIS that does the fitting. Of course, XSpec is not designed to do like lag fitting, lag frequency. So you have like KV versus energy all the time. But yeah, that's just if you like get rid of that, then yeah, you can fit with that.
But do you think do you think it would be better to have a separate software, like develop a separate software for this kind of stuff?
Well, I'm not an expert of fitting algorithm, but we have been using XSpec or ISIS for all this time. I think we can keep using that. So no, I don't know.
I think the challenge is because there are discussions going on about next generation spectral tools, mainly focused on things like Athena, for example, right? But the idea is multi-dimensional spectral fitting generically, and the question is whether you can convince the developers of the different spectral fitting packages to actually incorporate those. Because, you know, I get the feeling with some of the packages that it's really a case of just retrofitting, retro-engineering what they already have. Whereas sometimes to get more optimal things, you might have to just rebuild things from the ground up. And so there may be some resistance to doing that. I'm not sure. So I don't know whether we might have to start from not from scratch necessarily, but, you know, think more about specific tools for doing spectral timing modeling.
Well, personally, I fit energy spectrum together with lag spectrum in the same XSpec session without any, well, okay.
But you're not
yeah,
fitting simultaneously, you're still making choices about the frequency ranges that you're fitting those lag spectra to, for example, right?
Well, it's the frequency range where I extracted the data. So
yeah, but in principle, there's a lot more information because you could fit the entire cross spectrum as a function of frequency and energy, but you can't do that in XSpec because it only fits in one dimension.
Okay, yeah, but that's true, but you have a resolution in frequency anyway. So if you extracted the cross spectrum in 10 frequency bands, then you have 10 cross spectra as a function of energy, and you fit all of them together. That's what we've done for Sinus X1 and also the time average spectrum together. So I think it's a matter, you can extract the cross spectrum in like 20, 50 frequency bands, and then you have 50, actually 100 spectra, because you have real and imaginary part as a function of energy. Yeah, then it's impossible basically because XSpec is too slow to do it. It's 100 spectra.
So I see Ed on the Zoom, and so Ed, with the QPOs though, it's a different story. I mean, from what I see from your fitting, because it's really quite complicated having to deal with this GR, you know, the ray tracing and the. Could you say some more about that or how that works?
Yeah, so I mean, the model that we've got does work all like together. So at one point I put up an image of the various different fits I've got, and that's all like done in one session, modeling together. So like working together in XSpec, it works, given actually the Fourier transform things are in units of like counts and like your normal spectral energy, sorry. But so that does work. But yeah, there is the models that we run are slow in the way Expect calls them constantly. There are limitations there, most of which we can get around. But I have been actually talking to some people about potential like other fitting algorithms which potentially are better for when I've got a lot of parameters, which I know I've got. So there is potentially room for something different out there. It's just I don't think for a lot of people it's never been worth the time to do it. Whereas the hacking Expect has been easier.
It's worth. Things are changing a bit now because of new missions. So, for example, with EXTP, there's a push for solve because, of course, the quality of once you have a step change. I mean, right now we can get by with what we have, I think, with nicer data, for example. But once you get some sort of big step change in the quality of the data and also polarimetry, of course, timing polarimetry, then maybe you are at the point where you need to make a significant change in the way that you do it. So I mean, I know people, I mean, I'm included in that, but there are people who are also thinking about that from the point of view of new missions. So I guess that could kind of like, that's a good sort of wrap up point, is maybe the issue of the different, I guess the missions is one thing that's kind of already hopefully going to happen. I don't know what's happening from, if there's I know that for XBay there are developments for fitting polarimetry data in Expect. So I know that Keith Arnaud is building that in, but I'm not sure if there's any other initiatives to do with either the modeling or the, that are linked to missions. I guess we're still waiting for the decadal to find out about, for example, StrobeX. Can anyone comment on that? I think we have a few StrobeX people here, right? But I guess it's still a bit early for you to think about.
Yeah, I mean, I think from the decadal, what we're expecting is that they will say something about probe missions, but it's unclear whether they're, going to give any, nod to any particular one. But just saying that probe missions are supported would be a big step. But the time frame's pretty long, pretty long to launch.
Yeah, so overall, I get the feeling that a lot of the new developments are going to be basically tied to these big future missions, right? So okay, you're looking at Athena as being the one that's definitely on, kind of solid, right? But then we're talking the early 2030s, so that's a lot of time to think about it. So unless there's some big developments about, well, we have nicer data and we want to try and do more with it, possibly, or with the polarimetry side, I guess it's going to take a few more years, but we have time to work on it, I suppose. Does anyone else want to comment, or maybe Barbara to wrap up so we don't keep you?
So here in the room there is no one, I guess, but I have so as a scientist that analyze data, I have a question to people developing models. So basically to Guglielmo probably. So my question is, what do you think the limitations of current model are? And which are the steps that you think are doable in to progress in this, in a relatively short amount of time?
The limitations are several, I think.
For example, you use these linearization approximations.
Yeah.
So do you think this is a problem that should be phased at some point, maybe when data will get better?
Well, that's really technical. But personally, I think that's one of the last problem that we should face, because if these fluctuations are fast, as we see, is probably the linearization is good enough, and is basically the only way we can progress because you have to think that in order to fit a data set, we need to evaluate the model many times. I mean, you all know this. So the model needs to be super fast. And if it's not linear, then it's not going to be fast. So it's impossible to fit to the data. But I think that's not a problem. We have several issues about the geometry of the system. I don't want to keep saying the same thing, but the lamppost is not a realistic geometry. We need to think maybe like an extended corona, how it affects. And also the people that claim an extended corona, they use a lamppost to do the ray tracing for the reflection and the reflection lags. For example, model of Chris Dunn, she uses a lamppost in order to compute the light crossing time. So I think we have several limitations on the modeling point of view. And I think the best way to move forward is to use this model to the data, to the amazing data that we have with NICER, for example, also other telescopes, and see, okay, the model doesn't do a good job fitting the data, so then we need to address this. So yeah, I would encourage everybody to use the spectral timing models because yeah, I know I'm biased because I developed one, but yeah, I think it helps a lot who develop modeling to see where the model doesn't work.
Yeah, I guess maybe just to add that I'll make one final comment, which is that the Thomas Dowser made this point, that the point is we cannot explain what we're seeing in spectral timing data, right, in any completeness. So whereas the problem with the standard spectral fitting is that degeneracy, right, is that it's hard to distinguish all these different models that we already heard about this week. We actually have the opposite problem with the spectral timing, which suggests then that, you know, this is where it's even more important, right, to address, because while you might be able to get away with a lamppost corona in, you know, except for physical concerns in the standard spectral fitting with the spectral timing, I think we do have to have more realistic coronal geometries. But to do that, we have to be informed by the physics, right, by the models of corona coming out of the numerical simulations. So hopefully we can kind of square that circle a bit. I think that may be it from me. So
yeah, great. Yeah, no, we're over time a little bit, and I think we'll wrap it up there. Thanks a lot, Phil and Barbara, for leading the discussion, and thanks to Gulo for participating so much. We really appreciate that. And so yeah, so I'd like to bring the afternoon session to a close for today. Thanks to all the speakers as well. And we'll see everybody tomorrow.
Thank you so much. One small thing from the talk. First of all, if you can head over to the session 9 for Friday, Porshak, who's going to talk about multi-wavelength campaigns, has a question for everyone that he would like people to vote on. And the second one, please take a look at the talk, at the posters. I know they are online, but take a look. There's a lot of like cool results. All of them are linked both from the website and from the Slack. Contact the people the way you would do it if the posters were there in presence. Thank you, everyone. And I don't know, local announcements?
Just a quick announcement from the log. So for the people who plan to, yes, just a quick announcement from the log. So people who plan to visit Gallery downtown tonight, they should have received an email